you've sent over some really interesting research on multimodal large language models, or MLLMs for short.
Right.
They're a type of AI that can process both text and images.
Yeah.
Pretty cool, right?
They really are.
Yeah.
We're talking about AI that can answer questions about a picture,
Oh, wow.
generate captions, and even write stories
Really?
based on what it sees.
Wow.
It's taking AI understanding to a whole new level.
Okay, so
Yeah.
let's unpack this.
Yeah.
We're not just here to talk about how cool MLLMs are, though.
Right.
This research dives into a potential problem, something called data contamination,
Yeah.
that can happen
Right.
during their training.
Data contamination is essentially when a model has already seen some of the data it's being tested on.
Oh.
It's like peeking at the answers before taking a test.
Uh-huh.
Gives you a bit of an unfair advantage.
Yeah, definitely.
And it turns out
Yeah.
this contamination is a lot more common in the world of MLLMs
Right.
than we might think.
What's interesting here is that contamination with MLLMs isn't as simple as just seeing the same text, because these models work with both text and images.
Right.
You have two ways this contamination can happen.
The paper breaks it down into unimodal and cross-modal contamination.
Yeah.
Unimodal contamination is when the model has already seen the text part of the test.
Right.
Okay.
Imagine the model has been trained on a massive amount of text data.
Mm-hmm.
Then, during testing,
Okay.
it encounters a question that uses some of the same words or phrases
Right.
it saw during training.
Got it.
That's unimodal contamination.
So it's not that the model truly understands the question.
Right.
It's just that it recognizes the words
Yeah.
and spits out an answer based on what it's memorized.
Exactly.
Okay.
Now, cross-modal contamination
Yeah.
is when the model has seen the entire test item,
Wow.
the text, the image, and the answer.
Okay, now that's a whole other level of sneaking.
Precisely.
Yeah. And this type of contamination can have significant implications for how we evaluate these models.
Right.
If a model has already seen the test data, its performance is going to be artificially inflated.
And that makes it really hard to tell how well the model actually performs.
Right.
We could be fooled into thinking a model is incredibly smart when it's really just parroting back information it's already seen.
Exactly.
Yeah.
This issue isn't just theoretical.
Okay.
It has real-world consequences for how we choose and use AI systems. Imagine relying on a model for medical diagnosis or financial decisions,
Right.
only to find out later that its performance was based on contaminated data.
Not a comforting thought.
No.
So the researchers behind this paper didn't just identify the problem, they actually came up with a solution,
Right.
a framework they call Detect, which is specifically designed to catch this type of contamination.
The idea behind Detect is actually quite intuitive.
Okay.
It introduces small, almost meaningless changes to the test questions or images and observes how the model responds.
So it's like throwing the model a curveball.
Exactly.
Okay.
If it can handle the change, great.
Uh-huh.
But if its performance completely falls apart,
Yeah.
that's a big red flag.
If a model has truly learned the underlying concepts,
Right.
these minor changes shouldn't affect its performance too much.
Exactly.
But if it's relying on memorization,
Right.
even slight changes can throw it off completely.
Precisely.
To make things even more concrete,
Yeah.
the researchers used two specific techniques within this Detect framework. One's called the option order sensitivity test, and it's used for multiple choice questions.
Think of a typical multiple choice question with 4 options.
Okay.
A, B, C, and D.
Right.
With Detect, you would simply shuffle the order of those options
Okay.
and see if the model still picks the correct answer.
So if the model consistently gets the answer right when the options are in the original order, but then starts messing up when the order is changed, that's a sign it might have memorized the sequence
Exactly.
instead of actually understanding the question.
Precisely.
Okay.
And the second technique,
Yeah.
slot guessing for perturbation captions, is used for image captioning tasks.
This one sounds a bit more complex.
It starts with an image and a caption.
Okay.
For example, a brown dog is running in the park.
Right.
Detect identifies key words like brown, dog, and park, and replaces them with a mask. Mask.
Okay.
The model's job is to fill in the blanks.
Okay.
Now, here's where it gets interesting.
Here's where it gets really interesting, Amy.
You got it.
Okay.
The researchers take that original caption and use back translation
Okay.
They translate it into another language, say Chinese, and then translate it back to English.
Okay.
This creates a slightly altered caption that means the same thing, but uses different wording. Something like, a canine with brown fur is running through a green space.
Okay.
Then they mask keywords in this version.
Got it.
And ask the model to fill those in.
Okay, I'm seeing where you're going with this.
Yeah.
If the model could correctly guess brown and dog in the first caption,
right,
but fails when it sees the slightly rephrased version, it suggests the model has memorized the specific words.
Exactly.
Rather than grasping the concept.
It's a clever way to test if the model truly understands the image and its description.
Yeah.
Or if it's just relying on surface level patterns of the data it's seen before.
The researchers wanted to make sure that MMDetect was up to the task, so they did something pretty clever. They intentionally contaminated some models during training to see if their framework could catch it.
And the results were impressive.
Oh, wow.
MMDetect was able to successfully flag the contaminated models.
Okay.
Proving that it's sensitive enough to detect even varying degrees of data contamination.
That's a great start. But before we get ahead of ourselves, let's remind ourselves why this is such a big deal.
Right.
As we've said, contaminated models often perform better on tests, but it's an artificial boost.
And that raises serious questions about how we compare and evaluate different MLLMs.
Yeah.
If one model has been contaminated, can we really say it's better than another model that hasn't been exposed to the same data?
Right. It's like comparing apples and oranges.
Yeah.
Or maybe a better analogy would be comparing a student who studied the test beforehand to a student who didn't.
Right.
The one who studied is obviously going to do better, but it doesn't mean they're actually smarter or more capable.
Exactly.
And this has implications that reach far beyond just bragging rights in the research community.
Right.
It impacts how we choose and trust AI systems in the real world.
Okay, we've established that data contamination is a real problem.
Yeah.
MMDetect can help us identify it. And contaminated models perform artificially better on tests. But now I want to circle back to that fascinating discovery about contamination potentially being inherited from the foundational text-only language models.
Hold on, let me make sure I'm following this correctly.
Sure.
You're saying that the contamination could already exist in the foundational language model.
That's exactly what the research suggests.
Before it's even exposed to images.
They conducted a fascinating experiment where they gave these text-only language models questions that absolutely required visual information to answer correctly.
So questions like, what color is the car in the picture?
Precise.
Or is the cat sleeping or playing? Questions you couldn't possibly answer accurately just by analyzing the text.
And here's the kicker. Some of these LLMs, despite never being trained on visual data, actually got the answers right.
Whoa.
Yeah.
That's mind-blowing.
It is.
It's almost like these language models have some kind of sixth sense, some latent knowledge about images that they've somehow picked up along the way.
It's a remarkable finding that suggests that the massive data sets used to train these foundational language models might contain snippets of information that later appear in the data sets used to train MLLMs.
So even if we meticulously clean up the data used for multimodal training, there's still a chance that contamination is lurking in the very DNA of these MLLMs.
It certainly adds another layer of complexity to this issue.
That's a bit unsettling, wouldn't you say?
It does.
Yeah.
It means that addressing data contamination in MLLMs might require us to go back to the source to re-examine those massive text-only data sets and develop new methods for identifying and mitigating contamination at that fundamental level.
All right, we've covered a lot of ground in this first part of our deep dive. We've talked about what MLLMs are, the problem of data contamination, and even a potential solution with MMDetect. But we've also uncovered a surprising twist about the potential source of this contamination. What other insights did the researchers uncover? Take a quick pause here and then dive back in to explore the rest of this fascinating paper. All right, let's jump back into this research on data contamination in MLLMs. We left off on a pretty big cliffhanger. The possibility that contamination could be baked in from the very beginning, inherited from those massive text-only data sets used to train the foundational language models.
It's a fascinating twist that really highlights the interconnectedness of AI development. But before we get too deep into that, Let's take a step back and see what the researchers found when they actually put MMDetect to the test.
So they took MMDetect and ran it on a bunch of real-world MLLM.
Exactly. They tested 11 different models, including some big names you might have heard of. LLVA, GPT-4, Gemini, Claude.
Oh, wow.
Both open source and proprietary models were included in the study. The goal was to see just how widespread this contamination issue really is.
And what did they find? Was it as bad as they suspected?
The study found evidence of contamination in both open source and proprietary MLLMs.
Really?
It seems no model is completely immune to this issue.
That's a bit concerning. It sounds like data contamination is a pretty pervasive problem in the MLM world.
It is a challenge.
Were all the models equally contaminated?
That's a great question.
Yeah.
The degree of contamination varied across the models.
Okay.
Some were more susceptible to it than others.
Right.
And it wasn't just limited to older data sets either.
Wait, so even the newer data sets?
Yeah.
The ones specifically designed to avoid contamination were showing signs of it?
Yes. Even some of those newer data sets showed some evidence of contamination.
Yeah.
It really highlights how tricky this issue is.
Yeah.
And how important tools like MMDetect are for identifying it.
It makes you wonder if we'll ever be able to completely eliminate data contamination.
That's a good question.
It seems like a problem that might always be lurking in the background,
right?
Especially with those massive data sets that are constantly evolving.
It's definitely a challenge that requires ongoing vigilance.
Right.
And the development of even more sophisticated detection methods as the field of MLLMs advances.
Okay.
And these models become more complex.
Yeah.
We need to stay one step ahead of this contamination issue.
Speaking of staying ahead, remember those intentional contamination experiments we talked about earlier?
Yes.
The ones where the researchers purposely contaminated models to see if MMDetect could catch it?
Right.
Well, they took those experiments a step further and actually looked at how contamination impacts a model's performance.
That's a crucial part of this research.
Yeah.
It's one thing to be able to detect contamination. But it's another to understand its real-world consequences.
So did they find that contaminated models performed better?
Well,
I have a feeling I already know the answer to this.
As you might expect.
Yeah.
The contaminated models consistently scored significantly higher on the tests.
Okay.
But, and this is a big but, their advantage was deceptive. It wasn't based on genuine understanding, but rather on prior exposure to the test data.
It's like that old saying, you can't judge a book by its cover.
Right.
A contaminated model might look impressive on paper, but its true capabilities are a different story.
Exactly. And this difference in performance raises serious questions about how we compare different MLLMs.
Right.
If a model has been contaminated, can we really say it's better than another model that hasn't been exposed to the same data?
Right.
It's not a fair comparison.
Okay, so we've established that data contamination is a real problem.
Yeah.
MMDetect can help us identify it, and contaminated models perform artificially better on tests.
Yeah.
But now I want to circle back to that fascinating discovery.
Sure.
About contamination potentially being inherited from the foundational text-only language models.
Sure.
It feels like we're entering a whole new level of complexity here.
This is where the research gets really interesting.
Yeah.
Remember, they gave these text-only models questions that absolutely required an image to answer correctly.
Right.
Questions that should have been impossible to answer without visual information.
Yeah.
And yet, some of these models were still able to get the answers right.
It's like they have some secret knowledge about images hidden deep within their code.
It's really something.
How is that even possible?
The researchers believe that it's not about secret knowledge, but rather about subtle patterns in the data. It seems that those massive data sets used to train these foundational language models might contain snippets of information that later appear in the data sets used to train MLLMs.
So even if we meticulously clean up the data used for multimodal training, there's still a chance that some contamination is lingering from those early text-only training days.
Exactly. Wow. And this really underscores the need for a more holistic approach to data integrity in AI.
Okay.
We can't just focus on the final stage of training. We need to scrutinize the entire data pipeline.
Right.
Going all the way back to those massive text-only data sets that form the foundation of these models.
It's like realizing that a seemingly brand new house is built on a foundation with hidden cracks.
That's a good analogy.
It might look fine on the surface, but there are potential problems lurking beneath.
You're getting it. To really address this issue, we need to go back to the source and develop new methods for identifying and mitigating contamination at that fundamental level.
Okay, so they dug into the results from running MMDetect on these various models. They found a pretty widespread contamination issue.
Right.
And that it was having a real impact on model performance. Then they did this deep dive into the potential source of the contamination.
Yeah.
And it turns out it might go all the way back to the text-only data sets used to train the original language models. Now I'm really curious what can be done about this.
Well, that's where the researchers took on the role of detectives and actually tried to trace the contamination back to its source.
That seems like a pretty daunting task. I mean, we're talking about massive data sets with potentially billions of data points. How do you even begin to track down the source of contamination in something that big?
It's definitely not easy. They've focused on 3 common benchmark data sets used to evaluate MLLMs, Science QA, Kokio, Caption, and NoCaps. They compared these benchmark data sets to the training data used by various open source MLLMs, trying to find any overlaps or connections.
So kind of like a massive game of Where's Waldo, but with data points instead of stripes and glasses.
That's a great way to put it.
Yeah.
And they actually had some success.
Oh, wow.
They were able to categorize different MLLMs based on the likelihood that they had been trained on data from these benchmark data sets.
Okay, so how did they categorize them? What did they find?
They came up with a color-coded system. Some models were marked in red, indicating a high likelihood of contamination because they were directly trained on these benchmark data sets.
Ah, so those are the models that had basically been given the answers ahead of time?
Right.
No wonder they performed so well on the tests. But what about the models that weren't directly trained on the benchmark data?
Right. So there were also models marked in yellow.
Okay.
Which means there was a potential risk of contamination. Their training data included sources that might overlap with the benchmarks.
Got it.
But it wasn't a clear-cut case.
It's like those may contain traces of nuts warnings on food labels.
Right.
It's not a guaranteed allergy attack, but there's definitely a risk there.
Exactly. And then, of course, there were the models marked in green.
Okay.
These were the ones that seemed to be in the clear, at least based on the information that was publicly available about their training data.
So those were the models that presumably didn't have access to the benchmark data sets during their training?
Right.
That's good news, right? Or is there still reason to be concerned?
Well, even for those green-lighted models, there's still a chance of contamination.
Okay.
Remember, some models are trained on massive data sets that haven't been fully disclosed or vetted for potential overlaps with benchmark data sets.
And then, of course, we have to factor in the potential for unimodal contamination from those text-only language models.
Right.
Even if an MLLM hasn't directly seen a benchmark data set, the underlying language model might still be carrying traces of contamination.
It's like trying to bake a cake with all natural ingredients, but then realizing that your flour might have been contaminated with traces of peanuts from the factory where it was processed.
I like that analogy. It highlights how tricky this problem is to solve. Even if we're super careful about the data we use, there's always a chance that contamination could sneak in from unexpected sources.
And that's why this research is so important.
Yeah.
It's not just about identifying the problem. It's about raising awareness and prompting the AI community to develop solutions.
So what are some of those solutions? What can researchers and developers do to address this challenge of data contamination in MLLMs?
The researchers offer a few key suggestions in the paper.
Okay.
One of the big ones is the need for greater transparency and standardization in how we document and share information about training data.
You mean something like a universal nutritional label for data sets?
Exactly.
The way to quickly and easily see what's in a data set and any potential contamination risks.
Imagine if every data set came with a detailed report outlining its ingredients, potential allergens, in this case, benchmark data, and any known overlaps with other data sets.
Okay.
That would be a huge step in the right direction.
It would definitely help researchers make more informed decisions about which data to use and how to interpret the results of their experiments.
Right.
What else do the researchers suggest?
Another important suggestion is the development of more sophisticated tools for detecting and mitigating contamination.
So building on the work they've done with MMDetect.
Exactly.
Yeah.
MMDetect is a great starting point.
Mm-hmm.
But we need to continue refining these methods and developing even more robust tools that can handle the growing complexity of MLLMs and the datasets they're trained on.
Right.
And it's not just about developing new tools.
No.
It's also about fostering a culture of collaboration and knowledge sharing within the AI community.
So instead of everyone working in isolation and guarding their data and methods like trade secrets, we need more open communication and collaboration.
Absolutely. If we want to tackle this challenge effectively, we need to be willing to share information about potential contamination sources, collaborate on developing new detection methods, and work together to create a more robust and trustworthy AI ecosystem.
It sounds like addressing data contamination in MLLMs is going to require a multifaceted approach. It's not something that any one person or organization can solve on their own.
You're absolutely right. It's a complex challenge that requires a collective effort from researchers, developers, policymakers, and even users of AI.
Well, I think we've covered a lot of ground today. We've unpacked the problem of data contamination in MLLMs, explored the potential of MMDetect as a solution, and even uncovered that surprising twist about the source of contamination. But most importantly, we've started to think about what we can do to address this challenge and ensure that the future of AI is built on a foundation of integrity and trust.
That's a great way to sum it up. This research is a reminder that we're still in the early days of AI development, and there are many challenges that lie ahead. But with open communication, collaboration, and a commitment to data integrity, I'm confident that we can build a future where AI is a force for good in the world.
If you want to explore this topic further or dive into the technical details of MMDetect, you can find a link to the full research paper in the show notes. And be sure to join us next time for another deep dive into the world of AI. Until then, stay curious.